Okay, so we're going to be going through the second half of the Chapter 2 booklet. Let's begin with the vector equation of a plane. So if we think about a plane, to get somewhere on any plane, we need two vectors that are not parallel, say P and Q. Now, any point on this plane can move some direction in the P direction, and then, so that would be like S lots of the P vector, where S is a scalar, and then some lot of the Q vector, say T lots of Q. So to get anywhere on the plane, we go some multiple of P and then some multiple of Q, and we can get there, and that's uniquely defined for any point. If we're not on a plane where its corner is in the origin, then we're going to need to think about it a bit differently. So say we're trying to get to this plane, and then the origin is at this corner. Okay? We still have P and Q from before. Now the difference between the previous question and this question is we don't start on the plane. So in order to get to a point on the plane, we need to get to the plane first. And say to get to the plane, we just move from O to A, and that gives us vector A. And now we can move multiples of P and Q to get to points on the plane. So for any point on the plane, say R, which is X, Y, Z, we go to the plane first, which is doing A, and then we add multiples of P and Q respectively. So we can define any plane in this form. Okay? It's similar to the equation of a line, but now we're in two dimensions, so we need two vectors in the direction of the plane. Okay, example 6, you should probably pause the video, try this question yourself, and then see what you come up with. In this question, let's think about it. Well, we need to get to the plane first. We need to get to, so O to A, and then the vectors on the plane, they're going to be AB and AC. So we just need to find all these vectors. We do the obvious thing. Well, OA is the position vector, which is 1, 1, 1. AB is going to be going negative A plus B, or B minus A, which is this vector. And then AC is going to be negative A plus C, or C minus A, which is this vector. And so when you simplify everything, the vector equation of this plane is the following. Okay? And just to draw this, so we have O to A, and then we have a plane through the points A, B, and AC. So this is how we've thought about it. Next question. Find the point P where the line meets the plane. And the question is wrong, so just change the question to be 0, 1, 1 rather than 0, 0, 1. There's a typo there. So, in this question, we're looking for when are these things the same? When are the x, y, z values the same? So we just write them equal to each other. We've got column vectors here. So we can say the top row should be equal, the middle row should be equal, and the bottom row should be equal. So rearranging slightly, maybe pause the video now that you know how to do this, and see if you come up with the same things. But that's the top row. The middle row is minus 6k minus s plus t equals 1, and the bottom row is k minus s equals negative 3. And that's just from doing a bit of rearrangement with each row of the column vectors. And if we solve this first two equations, we can add the equations to eliminate t, which gives us s equals negative 2k. We can sub that value of s into the third equation, giving us k is negative 1. And then finding s, well, that just means s is 2, and then t is negative 3. So find the point P where it meets the line. Well, we know the k value now, so let's substitute that into r. So 2 minus 1, 2, plus negative 1 lots of 4, negative 6, 1, gives us negative 2, 5, 1, which is the point where the line meets the plane. You could check this substituting the s and t values into the point on the plane and see if you get the same value, and indeed you should. Okay. The coordinate then is minus 2, 5, 1. Okay, moving on. Eliminate the parameters s and t to find a Cartesian equation of the plane. So we looked at Cartesian equations of lines, and Cartesian equation of planes are similar but slightly different. So let's call this x, y, z equals The top row, 1 plus s plus 2t. The second row, 2 minus s minus t. And the third row, 3 minus s plus t. Okay. Let's call them equation 1, 2, and 3. And our goal is just to basically eliminate s and t. So if we do 1 plus 2, we get x plus y equals 3 plus t. Okay? And now from here, we can do, say, 1 plus 3. And we get x plus z equals 4 plus 3t. If we make t the subject of the first line, we get t, or, okay, if we make t the subject of, which one have we done? We've multiplied the top equation by 3 to get 3t equals 3x plus 3y minus 9. Okay? So it's multiplying the first equation by 3 and rearranging. And if we rearrange the bottom equation, we get 3t equals x plus z minus 4. And now we can just equate these. So 3x plus 3y minus 9 equals x plus z minus 4. And then rearrange and you get 2x plus 3y minus z equals 5. Now it's a Cartesian equation because you've got x, y's, and z's. And unlike the line equations where you had 3 equations equal to each other, here you can just have one equation. Okay. Okay, moving on. So, this is going to help us later with planes. Okay. So in order to describe planes in a new way, we're going to have to understand how we can describe straight lines, or something to do with straight lines. So consider a line, and it has a normal. So this vector n is normal to the line, and it passes through this point A, where we're given A as 1, 2, and r is the position vector of a general point on the line. So what can we say then? Okay, so we can say that n dot m equals 0 if 2 vectors are perpendicular. So now which 2 vectors are perpendicular on this line, or in this diagram rather? Well, the 2 vectors that are perpendicular are the vector r minus a is perpendicular with n. So we can say r minus a dot n is equal to 0. That must be true. So that means if we expand r dot n is equal to a dot n. Okay? R is equal to x, y, z, or x, y, sorry, because it's 2D. So if we look at what this means for this equation, for this specific case, we have x, y dotted with pq, because pq is the normal, equals 1, 2 dotted with pq. So when we do the dot products, we get xp plus qy equals p plus 2q. And then we go back. Okay, so here we have, if you look at this equation, we have some Cartesian things on the left-hand side of the equation, xp plus qy, and if we know the value of p and q, we'll get a number on the right-hand side. So we can see how this would work for in 2D. And this, in 2 dimensions, would describe a straight line. Okay? And it kind of looks like the Cartesian equation. It's a Cartesian equation of a straight line. And now what we're going to do is extend this to 3 dimensions. So let's do that now. Right, so this is just a plane, and we're going to draw on this plane with various points and normals. So let's draw the normal first. So n. Let's draw a point on the line r. And then this point, another point that we know is on the line, say A. So R is a general point on the line. And it's true that this vector normal to the plane is going to be normal to the vector R minus A. Okay? So we can say that R minus A dot n is still going to be 0. And n should be underlined, but forgive me. So R dot n is equal to A dot n. Okay? And now, if we were doing the dot product of the left-hand side, r being a general point x, y, z, dotted with a normal vector that we know, is going to give us the Cartesian equation. So this becomes a much quicker, easier way to find a Cartesian equation of a plane. Okay? Because rather than having to solve simultaneous equations, you just do a dot product. And then if you look at the Cartesian equation from before, we got the left-hand side was some coefficients with x, y, and z, and then the right-hand side was just a number. And a dot n, if you know a point on the plane and you know the normal vector n, a dot n is going to be a single value. Okay. Let's see if there's anything else here. Right, so this is just substituting in some values. So px plus qy plus rz equals a dot n, where a dot n is some number. Okay, let's move on. Let's try and apply this to some questions. So why don't you pause the video and see if you can apply this to this question. If you have paused the video and you tried, here is the solution. So r dot n equals a dot n. What is A? Well, A is going to be the vector, the position vector 1, 2, 3 as a column. R is a general point x, y, z, and n is 4, 5, 6. So when we do r dot n, you get x, y, z dotted with 4, 5, 6, which is 4x plus 5y plus 6z. And this is equal to a dot n, which is 1 times 4 plus 2 times 5 plus 3 times 6, which is 4 plus 10 plus 18. So 4x plus 5y plus 6z equals 32. So this is the vector equation, or sorry, the Cartesian equation of the plane, where n is the normal to the plane, and a, 1, 2, 3 is the position vector of a point on the plane. So it becomes very nice, very easy. Okay, moving on. The next example is a bit longer, because there are 3 parts to it. So, example 10. Find where a line meets a plane. Okay, so these questions are all going to be of the same nature. So if we write the x, y values for the point on the line, we get 1 plus 2t, t, and 1 minus 3t. Okay, and if we substitute these values for x, y, and z into the equation for the plane, we should find the t value, which is the point of intersection, or when the point of intersection occurs. So solving gives us 3 plus 6t plus 2t plus 4 minus 12t equals 11. So minus 4t equals 4, so t equals negative 1. So t equals negative 1 is when that intersection occurs. Substitute negative 1 in, and you get negative 1, 4 for the point of intersection. Okay, so for part B, if we go about it in the same way, we have our x, y, z values equals 1 plus 2t, t, and 1 minus 2t this time. Substituting these x, y values into the plane gives us the following. Now what should happen is we'll have a different end result. So if we look at what's happening, when we expand, all the t's are going to cancel, and we get 7 equals 11, which is what we're going to call inconsistent. Okay, and so since it's inconsistent, this suggests it's inconsistent, so there are no solutions to this problem. And so since there are no solutions, it suggests that the line is parallel to the plane. Okay? Next, if we look at the third one, it's the final version, and you can guess hopefully what the final version is. If we solve it in the same way, all the t's should cancel again, and we're left this time with 11 equals 11. This one is consistent, and so this suggests infinitely many solutions, which means that the line lies on the plane. Okay, so the difference between consistent and inconsistent in these cases, inconsistent means there are no solutions, so the line is parallel to the plane but not on the plane, and when it's consistent, there are infinitely many solutions and the line is on the plane. Not too bad. Let's move on. Okay, finding perpendicular distances. So this conceptually is quite challenging, but you can get to a stage where it becomes very quick to do. So we know n from the Cartesian equation of the plane here. So if we look at the question, let me look at the question again. Find the perpendicular distance of the point 4, 5, 6 from the plane x, 2y minus 2z equals 9. Okay, so we know the normal of the plane because if we look at the Cartesian equation, we've done x, y, z dotted with the normal. So this suggests that the normal n is 1, 2, negative 2. Check that you're happy with how we got that. Essentially, it's the coefficients because the coefficients represent the normal from the dot product. All right, let's draw a diagram which will help us to visualize this. So M is going to be a foot of P, where P is the 0.456, and that foot is perpendicular to the plane. Okay, let's call this angle theta. This is going to help us justify some of the distance formulas or distance stuff we're going to use. Okay, so PM, the length PM, is equal to PT cos theta, just by basic trigonometry. Okay. If we add some notation in here, so let's call the normal N. Okay, the normal could be going up or down, we're not quite sure. And let's give that purple line the vector PT. I think we're later going to call it P. So anyway, looking at a new formula, we know that N dotted with P is going to give us the magnitude of N, magnitude of P, cos theta, just by the definition of the dot product. Okay? So, the magnitude of P is the length PT from the previous equation. So, if we rearrange this purple equation, N dot P over the magnitude of N, this is going to be equal to P cos theta. Okay? Which, from the line above, from the line in that sort of tealy colour, N dot P over N, the magnitude of N, is going to be the length PM, because the magnitude of P cos theta is PT cos theta. They are the same thing. Okay? Now note, okay, T is any point on this plane. Okay? So all we need to find a vector P is to find any point we want to on the plane. Now there's a really nice way to find any point on the plane, and we just choose, say, y equals z equals 0. Okay? So if y equals z equals 0, then x is equal to 9. So the point O to T is the vector 9, 0, 0. That is definitely on the plane because it satisfies the equation for the plane. So now that we know that a point on the plane, we can find the vector P. The vector P is going to be negative OP plus OT. So it's 9, 0, 0 minus 4, 5, 6, which is going to give us 5 minus 5 minus 6. So this is the vector P. Okay, so what we've done is we wanted to find a point on the plane T in order to use it in the formula to find the distance PM. Okay, we need to find the magnitude of N at some point, so let's do it now. It's the square root of 1 plus 4, which is square root of 9, which is 3. Okay, so this is the length PM. So we can find the length of PM by doing N dot P. We've just found P, which is the point P to any point on the plane T, and we found the point on the plane T, 9, 0, 0. Divided by the magnitude of N, which is going to be 3. So it's a third of N dotted with P. Nice. So if we do that, we'll get a third of 5 minus 10 plus 12, which is 7 thirds. Okay, so this 7 thirds represents the length PM, which is the perpendicular distance, or the shortest distance, from the point P to the plane in the question. Okay, so this N dot P over N, where P is, where the vector P is the vector between the point we've labelled, or the 0.456 to any point on the plane, is going to be a useful formula that we're going to use in exams and other questions. So it's kind of a formula you need to know, and in this question we've tried to justify how we've got there. Okay. The next two questions are from example 12. So let's try those now. I'm going to stick on the same page because then I can use the same diagram, but you might want to turn to the next page if you don't have any more space. So the next question, example 12, is find the line through PM. Okay, so to do this, the question, so I just had a look at the question again. It's actually find the coordinates of the foot of basically find the coordinates of M from our diagram. So if we go, I'll have a look at the question again, and then we can talk about the question. So it says, find the coordinates of the foot of the perpendicular from the point P to the plane. So that is code in this diagram for finding the coordinates of M. So to do that, we're going to find the line through PM. Okay, so that's what we've written here. So to find the line through PM, we get to P, so O to P, which is 4, 5, 6, plus we're going to go in the direction of the normal 1, 2, minus 2. And then from here, what we have to do is just find the value of the intersection between this line, the line through PM, to the plane. And so we just substitute it in. So we know the equation of the plane, x plus 2y plus minus 2z. So we substitute the x value, the y value, and the z value into the equation of the plane, which gives us this. And here we'll find a value for lambda. So when we solve this equation, this gives us a value for lambda. If we skip a bit, so 2 plus 9 lambda equals 9. So lambda equals 7 over 9. So this is the value of lambda. And then to find the point M, we'll just substitute lambda in. So it's 4, 5, 6 plus 7 ninths of 1, 2 minus 2. And then when you solve this, you get 43 ninths, 59 ninths, and 40 ninths. So this is the point OM. This is when, this is the foot of the perpendicular of P to the plane x plus 2y minus 2z equals 9. Okay, so now we know OM. Another way to find the length PM, now that we know OM, well, there's two ways. We could find P to M and then find that length, but that's not the most efficient method. Okay? That is not the most efficient method. We know that PM is 7 ninths of the length of N. Okay? Because to get from O to M, we could go from O to P, and then, which is 4, 5, 6, and then we plus 7 ninths of 1, 2 minus 2. So we are going 7 ninths of the length of the vector n to get from P to M. So have a think about that and check that you understand and agree with that. So to get from P to M, we could go from P to M. Well, to get from O to M, we've gone to P, 4, 5, 6, and then we add 7 ninths of 1, 2 minus 2. To get from P to M, we're just doing 7 ninths of the vector n. So the length P to M is 7 ninths of the length of the vector n. And we know the vector n, it's 3. So it's 7 ninths times 3. So the length from P to M is 7 thirds using this method. It's just a different method. Okay, so we get the same answer as we did previously, but it's nice to have these two methods. Okay, so these are the two methods for finding the perpendicular distance or the shortest distance from any point from a point to a plane. Right, I think I'll stop this video here, and then we will do a follow-up, another video for the second part of this booklet.